Not all metals belong in water. Some can be dangerous. But what happens if we trap them in tiny chemical cages? Hello everybody, I'm Molly, and today I'll be talking you through the cages to trap metals activity. In this activity, we will complete an experiment to show how zeolites absorb molecules. This is based upon the activity found in the webpage linked below on the ChemBAM website. Here is the background. Teachers, if you're planning on using this as a part of a lesson, please feel free to show it. Most of the elements in the periodic table are metals. Metals have fascinating properties and are essential for our buildings, technological devices, and even our healthcare. Some metals are essential for our bodies to function properly. For example, iron in hemoglobin that transports oxygen in red blood cells. However, if certain metals get into our water supply, that can cause trouble. Some metals are toxic and can cause damage to our bodies. Metals can enter waterways in many different ways. Some leach in the groundwater from minerals that already exist in the Earth's crust. An example of this is arsenic, which is present in the groundwater of many countries and has caused many illnesses and deaths. Metals can also enter waterways via industry or consumers. This could be because of a lack of regulation, poor regulation, or accidents. For example, the Fukushima Daiichi power station in Japan that was damaged by the 2011 earthquake and tsunami. Following the work to cool the reactors with seawater, water in the harbour and groundwater was contaminated with radioactive elements. One way to remove metals from water is to use adsorbents. These can include activated carbons or zeolites. Zeolites are a type of crystalline solid material that occur naturally in the Earth's crust. They can also be synthesized in a laboratory. Zeolites are made up of silicon and aluminium atoms, which are connected together via oxygen atoms. These link to form a three-dimensional crystalline structure with molecule-sized tunnels and cavities that build cage-like structures. The 3D framework of zeolites can behave as cages that can be filled with ions. They are microporous, which means that they contain pores that are less than 2 millimeters in diameter. This means that they could absorb molecules and ions that are smaller than the size of the pore opening. The cage of the framework has an overall negative charge, and this negative charge is overall balanced by positively charged ions within this cage. The cations that can sit in this zeolite framework are mobile and can be exchanged with other cations. This schematic shows a blue zeolite framework that is negatively charged. The negative charges are balanced by the positively charged ions filling the holes. The red cations can be exchanged for other cations. Ion exchange works particularly well if the second type of cation has a higher charge. It can also work if the second cation has a better size match for the pore size in the zeolites. Ion exchange in zeolites is widely used in industry. For example, industry may use zeolites to remove toxic metals from their waste streams. This ensures that the water going back into the waterways is safe. Zeolites are also found in laundry detergents to reduce the formation of soap scum. Find out more about how ion exchange works in laundry detergents on the ChemBAM website, linked below. Zeolites and other cage-like molecules can be used to trap all sorts of ions, including radioactive ions. Researchers at the University of Birmingham study the way that zeolites and other porous crystalline structures can exchange ions with radioactive ions in order to clean up nuclear waste. Zeolites don't just trap ions. For example, they are also found in pet litter. The porous crystalline structures of the zeolites help by trapping unwanted liquids and odor molecules. Zeolites are also used as catalysts. For example, in the cracking process of alkenes. Again, it's the porous structure of zeolites that proves important. The many pores in zeolite's open structure are like millions of tiny test tubes where atoms and molecules can become trapped and chemical reactions are ready to take place. Since the pores in a particular zeolite are fixed on size and shape, zeolite catalysts can work selectively on certain molecules. So this is the experiment that we are going to do today. You might consider combining this activity with another one on the ChemBAM website. This is about looking at the removal of organic pollutants using carbon. The aim of this activity is to use zeolite to remove metal ions from a solution. This is what you will need. First, you're going to need some glass conical flasks, some copper sulfate and citric acid that we will make up into solutions. Universal indicator, the zeolite A powder, which is a 4 angstrom molecular sieve powder, a measuring cylinder, a stirring rod, a plastic pasture pipette, test tubes or vials, a spatula, filter paper, and weighing boats. So first I'm going to dissolve out the copper sulfate solution and citric acid solution. This can be prepared ahead of the activity if you are completing it as a part of the classroom lesson. So for each experiment you need 100 milliliters of 2% copper sulfate solution and 100 milliliters of 0.1% citric acid solution. So in order to make the copper sulfate solution, you need to measure out 2 grams of the copper sulfate and add it and dissolve it in 100 milliliters of water. So for 100 ml solution, I only need 0.1 grams of citric acid because it's a 0.1% solution. Okay, so the copper sulfate and citric acid are now ready to be used in the classroom. So now we can complete the experiment itself. Teachers, if you are looking to complete this as a part of your lesson plan, please either show this section of the video before or after the students have a go themselves, depending on what works best with your group. At this point, I am going to split my copper sulfate into 2 conical flasks, both with 50 milliliters each. I've labelled these A and B. A is our control solution. I'm not going to do anything to this. Then we're going to weigh out 1 gram of the Zeolite A powder. And then we're going to add this powder to glass P. And swirl for 5 minutes. So I've swirled this for 5 minutes. I'm now going to let this sit and settle so that all the powder goes towards the bottom.
At this point, you can then take 2 milliliters from each of the solutions and put it into a smaller glassware, for example a test tube or these little flasks that I have here. Try not to disturb the sediment in the glass B conical flask because this will interrupt the ion analysis. And as you can see here, the second one is lighter. Try to think about why this has happened. And then what we can do is we can scoop the zeolite sediment from conical flask B and put it on some filter paper and observe the colour the zeolite powder has turned. Now, I didn't think there was much of a difference between these 2 solutions, so therefore I added more powder and allowed it to mix more to see if I can enhance this effect. As you can see here, this decolorised the solution further.
There are a set of questions in the activity pack on the ChemBAM website that I would recommend completing now. 2 extra questions can be completed if you complete the extension activity, which I will show you now.
For this next activity, we're going to add 0.5 milliliters of universal indicator solution to 100 milliliters of the citric acid solution. Then we're going to divide this between 2 conical flasks, adding 50 milliliters to each. Before we move on, note the colour and the pH of this solution. We're going to keep the first flask, flask C, as a control flask, and then we're going to add 1 gram of the Zeolite A powder to flask D. Sometime to get all of the powder into the conical flask, I flick the weighing boat to make sure it all drops in, and as you swirl for 1 minute, note the colour change. After this, allow it to sediment for 5 minutes. Once again, take 2 milliliters from the top of the solutions from both the conical flasks to compare the colours between the 2. As you can see, our control has not changed colour because we've not done anything to it. However, flask D has turned more yellow. Why could this be?
So zeolites are really cool substances. Let's look at how they are currently being researched in laboratories. Once again, feel free to show this as a part of your lesson. Researchers at the University of Birmingham are using zeolite-type structures of porous materials to exchange ions with radioactive ions that are found in nuclear waste. Researchers have recently looked at the ion exchange of radioactive isotopes of cesium of using cage-type crystalline structures, similar to zeolites. Radioactive cesium is produced during uranium fission in nuclear reactors, and it is also the main medium-term health risk remaining from the Fukushima accident. Ion exchange is performed by passing contaminated groundwater containing the radioactive ions through columns containing porous zeolite-type structures. Once used and full of radioactive ions, these columns are then classified as high-level radioactive waste and need to be safely stored. The ions are mobile and the exchange is reversible. So once trapped inside the cage structures, how do we stop them leaching out? Researchers are currently investigating how the chemical structure of the cage-like materials can be changed using heat and pressure to lock the ions in place permanently using a process called hot isostatic pressing. I hope you enjoyed this fun activity. Please check out the other experiments, videos, and resources on the ChemBAM website linked below. And if you have any questions, feedback, or would like to request a visit, please use the Contact Us section on the website to get in touch. There are also some other videos that ChemBAM has recently made, so if you are interested, please check out our YouTube channel. Thank you so much. Bye!